Hello everyone, and welcome to our Group 16's presentation for PRT 565 Assessment 3. Our project is titled Epileptic Seizure Recognition using Machine Learning and Deep Learning Models. My name is Shibi Turag, and I will begin by explaining the background, motivation, and dataset used in our study. So, moving to the introduction part, epilepsy is a neurological disorder characterized by sudden and unpredictable seizures caused by abnormal brain activity. Traditionally, neurologists analyze EEG signals manually to detect seizures, but this method is time-consuming, complex, and prone to human error. Our motivation behind this project was to design an automated seizure detection system using artificial intelligence or AI that can help doctors make faster and more accurate diagnoses. Such a system can save valuable time, reduce misdiagnosis, and make healthcare more accessible, especially in remote areas where neurologists may not be available. In short, our goal is to make seizure detection faster, safer, and more reliable using machine learning and deep learning. Moving to the aim of the project part, the main aim of our project is to develop and compare several AI-based models for epileptic seizure recognition. We implemented three machine learning models, decision tree, random forest, and naive Bayes, and one deep learning model, the artificial neural network, ANN. Each model was evaluated based on accuracy, precision, recall, and F1 score. We also explored more advanced deep learning architectures like long short-term memory or LSTM and recurrent neural networks or RNN, which are particularly effective for sequential EEG data. Through this comparison, we aim to identify the most suitable model for accurate and efficient seizure detection. Moving to the dataset description part. For this project, we use the Epileptic Seizure Recognition dataset from UCI Machine Learning Repository. It contains around 11,500 EEG samples, each with 179 features and one target variable that indicates seizure or non-seizure activity. The data was recorded over 23.6-second intervals from different brain regions. This dataset is ideal for binary classification, allowing us to test both traditional and deep learning methods fairly. So the next parts are data preprocessing and machine learning models will be described by my teammate Mahmoudou and Daniel. Thank you.
Thank you, Shibir, for his speech. From here, we will talk about the data processing and feature engineering that has been used in this analysis. Myself, Mahmoud Rahman. Before our training our model, we perform several data processing steps to ensure that our electroencephalogram data was consistent and reliable for machine learning analysis. First, we remove unnecessary or redundant column that did not contribute meaningfully to the seizure prediction. Next, we normalize all numerical features using standard scalar so every variable contributed equally, avoiding biases from features with larger numeric ranges. We then encoded the target variable, assigning 1 for seizure and 0 for non-seizure, turning it to a binary classification problem. Finally, we split the dataset into 60% training, 20% validation dataset, and 20% testing sets. This structure helps us to train, fine-tune, and evaluate model objectively, ensuring that what we learned wasn't just memorization, but genuine pattern recognition. All processing was implemented efficiently using pandas, NumPy, and scikit-learn. Uh, Moving to our next slide, here our first ML model, the decision tree classifier. Our first model was a decision tree, a simple yet powerful algorithm that works like a flowchart of questions. It splits data based on feature threshold, forming branches until it reaches a final destination that classifies the signal as seizure or non-seizure. The strength of decision tree is interpretability. We can clearly see which EEG feature influences each decision. However, trees can sometimes overfit. They may learn noise rather than just a real pattern. So we later addresses these two ensemble techniques. Moving to our next slide is random forest. It's a powerful ML model. It's especially in assemble of many decision trees. Instead of relying on a single tree, it builds multiple trees on random subsets of data and features that average their predictions. This reduces variance and makes the overall model more stable and accurate. The random forest captures subtle electroencephalogram signal pattern that a single tree might miss, improving our generalization and reducing the risks of overfitting. Moving to our next slide, we use here Naïve Bayes classifier. Uh, Naïve Bayes is a probabilistic classifier algorithm based on Bayes' theorem, which calculates the probability of a class given certain feature. It also assumes that all features are independent on one another, a native assumption that it simplifies computation. And also, we uses a deep learning model uh, to push beyond our classical machine learning model. We develop a deep learning model using an artificial neural network. This approach mimics how the human brain processes information through layers of interconnected neurons that learns pattern automatically. Our AN model began with input layer of 179 neurons corresponding to each EEG signal. Then we added multiple hidden layers that we can use ReLU activation function. This helps the model learn complex nonlinear pattern that a simple model cannot capture. Finally, our output layer, we used a sigmoid activation function, reducing a probability between 0 and 1, where values close to 0 represent seizure activity and 0 represent non-seizure activity. We trained our AN model using Adam optimizer and binary cross entropy as the loss function. Together, this ensures fast convergence and accurate learning during training. Compared to decision trees or naive Bayes, our artificial neural network demonstrated a stronger ability to generalize, especially when the electroencephalogram signals had overlapping or noisy patterns. However, one limitation was that it didn't fully capture temporal dependencies. That's why seizures pattern evolved over time. To address that, we turned to a sequential model called LSTM. It's a long short-term memory. The long short-term memory, or LSTM, is a specialized type of recurrent neural network designed for sequential data such as electroencephalogram signals, where time and order matter. Unlike standard neural network, LSTM include memory cell and three key gates like input, forget, and output gate that control how information is stored, forgotten, and passes forward in time. This mechanism allows the LSTM to remember important sequence pattern that occur several time steps earlier, such as gradual changes in brain activity leading to seizure. In contrast, a traditional model treats every input independently, missing this crucial temporal context. During training, the LSTM achieves significant improvements in accuracy and recall, especially for longer seizure sequences. It effectively learns how EEG signals intensively fluctuate over time and how those changes indicate possible offset. Next, our third team member Daniel will continue from there. Thank you.
For explaining your part. And I'm going to start with model performance evaluation. And my name is Daniel, and I'm going to explain about the decision tree. So it has a 46.3% accuracy, and it works by splitting data based on feature values, creating a tree-like structure where each branch represents a decision rule and each leaf node represents predicted classes. And it has accuracy of 46.3% and a macro precision of 0.5043 and a recall of 0.4630 and an F1 score of 0.4468. And like it struggled to generalize across all EEG classes, particularly due to overlifting. And the second one is random forest. So our second model was the random forest, which is an ensemble of multiple decision trees. It improves stability and accuracy by averaging the prediction from like several trees, reducing the risk of overlifting. And it has an accuracy of 72.5% with a macro precision of 0.7229 and a recall of 0.7252, and it has an F1 score of 0.7221. Like this model consistently performed very well across all EEG classes, demonstrating its ability to handle complex and high dimensional data. And like overall, random forest was most reliable transcendental machine learning model in our study. And the next one is I'm going to explain the Naïve Bayes model. So it's an algorithm which is based on Bayes theorem, and it has an accuracy of 44% and a macro precision of 0.4370 and a recall of 0.4400 and an F1 score of 0.4176. It performed very well on some classes but struggled with like correlate ESG features. Although its performance was lower than random forest, it provided a useful baseline and show the trade-off between speed and accuracy in model acceleration. And the third one is deep learning model, which is ANN, which stands for artificial neural network, and it does like many works, and it all written by layers with ReLU activation and an output layer of sigmoid activation for binary classification. So we have trained model using Adam optimizer and binary cross entropy loss function. So it has an accuracy of 67.1% with a Persian of 0.6893 and an F1 score of 0.6597. It performed very well, like recognizing seizures patterns, and did not like surpass the random forest. And the next one is LSTM model, which stands for long short-term memory model. So which is a type of recurrent neural network RNN, and it has a design for SQL data such as ECG signals, and it has an like accuracy of 55.8% with a macro precision of 0.5788 and a recall at 0.5578 and an F1 score of 0.4786. Like it performs strongly on classes 1 and 4, but it like less worked on classes 2 and 5 because of its overlapping non-seizure signals. And the next one I'm going to explain about the conclusions. So our project concludes that the potential of artificial intelligence in automating epileptic seizure detection. So among all the models, I state that the random forest was the most accurate and reliable because of its accuracy. However, deep learning models, like particularly long short-term memory models, showed promises for future work by effectively utilizing the sequential nature of EEG signals. And like the overall study highlights how AI can make seizure recognition faster, more accurate, and more accessible utility, supporting the doctors and improving patients' care worldwide. And the last one is references. So we have references from UCI Machine Learning Repository thing, and libraries such as we have used skitlearn, TensorFlow, Pandas, and Matplotlib. And like we have shared the link which all the images are like gathered from that one. So this is our references. So thank you everyone. Thank you.